Hello again, welcome to the second lecture of week 6. So what are we going to do today? In this lecture, we're going to look at logic coverage criteria again to test code. So if you remember last time I told you that logic coverage criteria when it comes to testing code is very important, and to be able to understand the problems related to reachability and controllability well, I will walk you through two examples that illustrate the use of logical coverage criteria over source code. In the last lecture, we did the example of thermostat. There was one large predicate with 4 clauses in that example. We showed how to solve for that predicate. That predicate had a clause with an internal variable, how to reach that predicate, how to solve for it, and how to write test cases for predicate coverage. We also saw how to write test cases for correlated active clause coverage for that predicate. In today's lecture, we'll take another program, which is a very popular program that you will find in a few other textbooks in software testing, to test for decision coverage or logic coverage. And I'll tell you how to apply the predicate coverage criteria that we have learned to be able to do testing for that program. That program is about detecting the types of a triangle. So this is a program that I have taken from the textbook first edition of Paul Amman and Jeff Offutt. The authors wrote this program. In other books you might find the control flow graph corresponding to a program, and this program basically is called TriType, in short for type of a triangle. And it detects these 3 types of triangle, or it says that it's not a valid triangle. So the triangle could be a scalene triangle, in which case all the 3 sides are of different length than a scalene triangle. In an isosceles triangle, 2 of the 3 sides have the same length. In an equilateral triangle, all the 3 sides have a same length. Let's say if one of the sides that is entered is a negative number, then this program will output saying that a triangle that you're trying to give as input in 3 sides is not a valid triangle. Here is the program. So what it does is that it has 3 integer variables a, b and c represented to be taken as inputs for the 3 sides of a triangle, and then it has an integer t. We'll see what this does. T is for giving the output. T returns the output, which is the type of a triangle. So the 3 sides of a triangle are taken as input here. So the first side is taken as input in A, the second side is taken as input in B, the third side is taken as input in C, and then this main program calls this method called triang with inputs A, B and C as the 3 sides. This triang runs its code. I've given you the code for triang in the next few slides, and returns a number to be stored in T, and then the system output saying the result is T. So T is a number that represents one of these 3 types of a triangle, or T could be a number that says that it's not a valid triangle. So here is the main triangle classification method, this one, triang. As I told you, code will be presented over several slides. Please read it as a contiguous fragment of code, and from end to end the code may not be executable. We are concentrating only on the fragment as it's relevant for us to be able to understand test case design. So this is the second slide containing a continuation of the same code. It has triang method. So here is what it outputs. It has an internal variable within this method called tryout. Tryout is the output from that method. So what does it output? It outputs 1 if the triangle is a scalene triangle. It outputs the number 2 if the triangle is isosceles. It outputs the number 3 if the triangle is equilateral. It outputs 4 if 3 sides constituted that were entered don't constitute a valid triangle. So what we first do here in this method is we first check if the triangle is valid or not. Why will it not be a valid triangle? It will not be a valid triangle if one of the sides is, let's say, of negative length. So that's what this if checks for. It says if side 1 is less than or equal to 0, or side 2 is less than or equal to 0, or side 3 is less than or equal to 0, then you set tryout to be 4. What does tryout to be 4 mean? If you go above and see, tryout 4 means that it's not a triangle. So you set tryout to be 4 and return tryout. So here basically after taking the 3 sides as inputs in A, B and C, they get passed to the triang method A, B and C. Triang method takes them as inputs side 1, side 2, side 3. First thing that it checks is if any of the sides is less than or equal to 0. That's this if statement in line number 18. If any of the 3 sides is less than or nor equal to 0, it sets try out to 4, which we interpret in the code to mean as it's not a valid triangle, returns it and comes out. Now after this, it's ruled out the fact that it's not a valid invalid triangle. From now on, it's working with a valid triangle. It just has to find its type. So what are the three types that the code can output? The three types that the code can output are whether it's a scalene triangle, isosceles triangle, or an equilateral triangle. If it's a scalene triangle, it outputs 1. If it's isosceles, it outputs 2. If it's equilateral, it outputs 3. This is how the code is written. So here is the rest of the code, which determines which of the three types the triangle is and outputs the corresponding number. So another thing that I would like to tell you is that the style in which this particular code is written is slightly long drawn and complicated. You could directly maybe write a simpler code that will directly detect the type of the triangle to be one of the three types. By no means is this code the shortest length code or the simplest code to detect the type of a triangle. It's written in a slightly roundabout way with lots of predicates labeling various if statements just to illustrate the richness of logic coverage. Remember, we are using this example to understand logic coverage criteria better. So this code is written in a slightly long way, started with a lot of predicates one after the other, so that we could use it to understand logic coverage better. But it's the same thing which still correctly computes which is the type of the triangle. So if it is not 4, which means if it's not a valid triangle, the code continues here. It sets try out to be 0, and then what it does, it takes one side after the other and compares to see if it's equal. So let's say if side 1 is equal to side 2, it increments try out, makes it 1. If side 1 is equal to side 3, it increments try out, makes it 2. If side 2 is equal to side 3, it increments try out and adds 3. Right, so by then it would have correctly computed if all three sides are equal, then all the three if conditions would have passed and the value of the variable try out would be 3 correctly. If try out is 0, then what it does here is it checks again. So it says if side 1 plus side 2 is less than or equal to side 3, side 2 plus side 3 is less than or equal to side 1, or side 1 plus side 3 is less than or equal to side 2, there's a problem, right? It cannot be the case because this violates the property of a triangle. So it outputs saying it's not a valid triangle. Else it says yes, it's a scalene triangle. So this comment says that it basically confirms that it's a valid triangle before declaring it to be scalene if try out is 0. And it returns once it computes. Now in this part, it's trying to compute whether, trying to figure out whether the triangle is isosceles or scalene. So let's say try out value turns out to be greater than 3. It says if is equal to 3, then you directly set it to be 3 and output. Otherwise, now you check if it's equilateral or not, which means you check if sum of two sides is greater than one side. These are the three ways in which sum of the two of the sides could be greater than the third side. Those are the three conditions here, and the corresponding values of the tryout are given here. In all the cases, it sets tryout to be 2 because that's what it has to output to if the triangle is scalene, and it returns that. Otherwise, it says if any of these conditions are violated, then it says it's not a valid triangle and returns it. So that brings us to an end of the code. So in summary, what does this program have? It program has 3 input variables A, B and C in the main program method. The 3 inputs are passed as formal parameters to the triangle method as side 1, side 2, side 3. Triangle method has an internal variable called tryout, which is set to the value t to be returned back to the main method. So all these predicates, so if you see there are so many predicates in this triangle method. The first predicate that you encounter is here at line number 18, which is this. And then we have 3 more predicates here at lines 22, 24, 26 and 28, fourth one. Each of these 4 predicates have exactly 1 clause each. In line number 29, there is 1 more predicate with 3 clauses. And here again in lines 33, 35, 37 and 39, there are 4 more predicates. So here is where we have listed all the predicates as they come in the code. At line 18, there was this predicate which checked whether the triangle was valid or not. And then this was the part where it starts building towards checking if the triangle is isosceles or equilateral. and if it was a scalene triangle, it outputs this. Now it does to check if it's a valid triangle in line 29, and then these are the parts where it checks whether it is isosceles or equilateral triangle. So this slide, what I have done is we've gone through the code here, pulled out all the predicates from the code with their line numbers and just listed it here, right? So if you find it a little fast, you could move back and forth between the code and this and check if the predicate and corresponding to each line has been correctly listed in this code. After this, what we want to do, so this is the set of full predicates that we want to work with. So you can be ambitious and you can say that I will attempt each of the logic coverage criteria that we learned for each of the predicates here, right? You could do that. If you try to do that, you'll realize that for these predicates, the predicates in lines 22, 24, 26, 28, and the one in line 33, how many clauses do each of these predicates have? They have only one clause, right? Because they have no Boolean operators in between them, and each of these predicates, the whole predicate is just one clause. So if you remember, for predicates with one clause, just predicate coverage is enough, because you really can't do anything much. For other kinds of coverage criteria, you need more than one clause in the predicate. So for each of these predicates, you could directly write test cases that will test the predicate to be true once and false once. In fact, please try and do that as a small exercise for these predicates, the predicates in lines 22, 24, and 26, because you just have to give three values of sides, such that here for 22, side 1 is the same as side 2, and for 24, side 2 is the same as side 3, and for 26, side 3 is the same as side 1, and then you're done. But for predicates in lines 28 and 33, you have to be able to give a value of tryout. Where does tryout come? Let's go back and look at the code. Tryout is an internal variable that belongs to this method, triang, which is the main triangle classification method. So these predicates in lines 28 and 33, which have only one clause which deals with tryout, deal with an internal variable. But what are the main inputs to the program? The three sides of a triangle. So to be able to test this predicate, let's say tryout is equal to 0, I need to be able to give values for the three sides such that tryout is equal to 0 becomes true when the predicate should be true, and I should be able to give values for the three sides, side 1, side 2, and side 3, such that tryout is a value not equal to 0 for this predicate to be false. Similarly here, for line 33, I should give values for inputs sides 1, 2, and 3 such that tryout becomes any value greater than 0, which means it could take 1, 2, or 3, or 4. It could even be an invalid triangle. To make this predicate false, I must make tryout to be precisely equal to 0, which means I have to be able to give values in terms of inputs, which are sides 1, 2, and 3. So what we have to first do is we have to be able to find out reachability of the various predicates. So from these slides onwards, so this is the exhaustive list of all the predicates in the program. From these slides onwards, I have illustrated the subsequent concepts: reachability, solving for the internal variable, computing coverage criteria. I have illustrated it only for a subset of the predicates, mainly because it's a repeat exercise if I want to be able to do it for all the predicates. And for you to be able to learn, it will be good if you can work it out for one or two predicates on your own. In particular, I haven't done for these predicates in lines 35, 37, and 39. So feel free to work them out as a small exercise that you could do for yourself. So what is the reachability of predicate in line 18? The predicate in line 18, if you go back to the program, happens to be the first predicate. So it will always be reached because that's right, the first statement in the method. So the reachability for that is true. Means it will always be reached. There's nothing else you need to do. Now let's look at the next predicate in line 22. As I told you, to be able to reach here, you have to be able to give any values, side 1, side 2, side 3, such that the predicate in line 18 is skipped. This if statement doesn't come and doesn't exit the method from here. If you don't want the method to exit from here, you should be able to give values for side 1, side 2, and side 3 such that this if condition is false. Once that becomes false, you come here and you start executing the other predicates. That's what is written here. It says in line 22, for me to be able to reach, I must give side 1 to be greater than 0. I have abbreviated as side 1, SIDE1 as S1, just to make it fit neatly into a slide. Similarly, side 2 is abbreviated as S2. Side 3 is also abbreviated as S3. And this whole thing, we've gone ahead and called it as P1. This is a new notation that I'm introducing now, so that I could write P1 here for reachability of predicates, lines 24, 26 and 28. So lines 24, 26 and 28, each of these predicates can be reached provided the values of all the three sides of the triangle is greater than 0. That's what it says. Now for line 29, I should get values of all the three sides greater than 0, and in addition, the internal variable tryout must be equal to 0. Now line 29 was an if part with an else part, which I didn't give a line number for. Let's go back to the program. If you see, this if part has this else part, which I didn't give a line number for. So the reachability for that is the negation of the reachability for line predicate in line 1. So which means that it is this and these things are true. So now I continue and list reachability conditions for each of the other predicates. In each of these conditions, I must be able to skip past line number 18, which is P1, and then write appropriate conditions. If you see, all these appropriate conditions deal with an internal variable tryout, and there is a condition on the value of tryout. This one says tryout should not be equal to 0. This one says tryout should be less than or equal to 3. This one says tryout should not be equal to 3. This one says tryout should not be equal to 1, and so on. So we need to be able to solve each of these predicates for the internal variable tryout. In particular, we need to be able to give values for the three sides A, B, C, or 1, 2, 3, such that here in line 33, tryout turns out to be not equal to 0. In line 37, tryout turns out to be less than or equal to 3, and so on. So how do I solve? This is the table that tells you how to solve for the three predicates. So if you go back and look at the program and see, when will the variable tryout take the value 0? It will take the value 0 if all the three sides are not equal to each other. So that's what is this condition. It says tryout will be 0 if side 1 is not equal to side 2, and side 1 is not equal to side 3, and side 2 is not equal to side. So similarly, tryout will be 1 if one set of sides are equal, let's say side 1 is equal to side 2 and the other two are different. Similarly for 2, 3, 4, 5 and 6. Right? These are the values that tryout will take. Now what I do is I go back and take this predicate in line number 29. It says P1 and tryout is equal to 0. So for tryout to be 0, this is the condition that I have written out. This is the condition for reachability and controllability for tryout to be 0. So I take that and substitute it back here. Now what I have achieved? I have achieved in rewriting the predicate that comes in line number 29 purely in terms of inputs to the program. The predicate P1 was in terms of the three sides, and the fact that tryout was 0, I have removed that and rewritten it as another predicate that exactly will map to tryout being 0. So this is the predicate that I take and test for predicate coverage or clause coverage or correlated active clause coverage or whatever coverage criteria that I want to apply, whatever logic coverage criteria that I want to apply. This is the predicate that I will test it for. What have I achieved in this predicate? What I have achieved is that I have achieved in completely eliminating the internal variable tryout from this program. I have rewritten the predicate to be purely in terms of inputs and outputs. So whatever coverage criteria I want to be able to do this in predicate, now it becomes easier for me because I can directly give values to the three sides such that each of these clauses have true false values to achieve my desired coverage criteria. Similarly, the second item here, for the else statement of line 29, I have gone ahead and replaced the value of tryout to be 0 with this rule in the table. So I've directly gone ahead and substituted. That gives me this long looking predicate. And I go on doing this for each of these predicates, right? Each of the predicates in this slide, lines 33, 35, 37, 39, else of 39, all of them have specific values for tryout. So I go on removing those tryout not equal to 0, tryout is less than or equal to 3, and replace it with appropriate values and finish. I have not given them, but you can complete that by substituting it. Now, what I have done, the set of predicates that I have here, when I complete that set fully, is all the predicates in the program with no internal variable in it. The predicates directly talk about the conditions on three sides and what are the values that each of these conditions will represent. I am ready to apply all my logic coverage criteria on these predicates now. So what are the various logic coverage criteria that I have to apply? So for example, I have taken the predicate in line 18, which was like this, and this is the table that tests for predicate coverage for each of these predicates. I have given you again only a subset of the predicates. You can write test cases for other predicates also. How do you read this table? This first column here gives you the line number in which the predicate comes in the program. The second column actually lists what the predicate is, and these represent test case values for predicate coverage. The first set of values here test when the predicate is true. The second set of values here test when the predicate is false. So you give inputs A, B and C. I'm sorry, there's a small error here. Read this B that I'm pointing to as C. And then what's EO represent? EO represents expected output. So it says if the inputs to the three sides of a triangle A, B and C are these three, then the expected output should be 3. And if the expected output is 3, then predicate coverage is tested for being false. So similarly, predicate coverage is tested for being true. All the three triangles have input 0. The expected output is 4, which means it's not a valid triangle. So similarly, for predicate in line 22, which is S1 is equal to S2, I have given some value here, and the output here should be correctly, if you see all the three values here are the same, so output is an equilateral triangle. Here the output is false, so it is only two sides are equal. Similarly for here, it is predicate is true, again predicate is false, right, because side 1 is different from side 3. Now in line 29 we had this predicate S1 plus S2 is less than or equal to S3, or S2 plus S3 is less than or equal to S1, or S1 plus S3 is less than or equal to S2, and these are the test case values that will test for the predicate being true. This is the expected output, and for the predicate being false, these are the test case values, and this is the expected output. So here for some of the predicates in my triangle program, I have written test cases for achieving predicate coverage for both true and false. So similarly, we can do clause coverage. We didn't do clause coverage for the thermostat example in the last lecture. That predicate also had 4 clauses there. Just for illustrative purposes, I have done clause coverage here for some of the predicates. Please remember one point that we discussed a little while ago in this lecture. If a predicate has only one clause, then that doesn't make sense to do clause coverage. So a predicate should have more than one clause to be able to do clause coverage. So I have taken 2 example predicates that have more than one clause. The first one is the predicate in line number 18 that had 3 clauses. S1 less than or equal to 0, first clause, S2 less than or equal to 0, second clause, S3 less than or equal to 0, third clause. Again, in the same way, read this whole thing. These are 3 sides of the triangle, expected output. For the clause coverage to be true, this clause to be true, these are 3 sides of the triangle, expected output for this clause to be false. Similarly, for the predicate in line 29, there are 3 clauses, and these are the test cases that will test for each clause to be true in turn and each clause to be false in turn. Similarly, for all of the predicates that have more than one clause, you could go ahead and write clause coverage. Now I have attempted correlated active clause coverage for the predicates. Here again, to be able to do, consider a predicate like this in line 18, S1 less than or equal to 0, or S2 less than or equal to 0, or S3 less than or equal to 0. It has 3 clauses. You have to make each clause the major clause in turn, make it determine the predicate. That is, assuming that this is A, compute P subscript A, and assuming that this is B, compute PB, and assuming that this is C, compute PC. Then you populate a table that looks like this, which makes the first clause true and false, second clause true and false. Then you have to eliminate duplicate rows, and then finally you will get this set of true false values. I have skipped all those steps, but I advise you to strongly try and do that. It will be a good exercise in revising how to make each clause a major clause and make it determine the predicate, and prune the truth table by removing the rows that occur as repetitions. Once you do that, you will realize that you will be reduced with just these 3 rows. The first row makes clause A true. A is the major clause. clauses B and C false. Here is a set of test case for that. Here is the expected output. Second row makes clause A the major clause. This time it's false. B and C are false again. Here are the inputs. Here is the expected outputs. Similarly, for this this predicate also we have done this. So hopefully the second example would have helped you to understand how to do various logic coverage criteria for predicates in a fairly large program. This program that detected the type of a triangle was a fairly large program. It had several predicates. Feel free to write to me on the forum if you want have any doubts, or if you're not able to complete some of the coverage criteria. Try them out and write to me. We'll be happy to answer any questions. Thank you.